Okay, this is the recording of lecture number 13 for Geology 2017. In the last few lectures we started to really address sedimentary rocks. So in the last, in particular, we were really discussing about sedimentary structures. So in this new lecture we are going to take those sedimentary structure and find context for them. So you will learn essentially information that pertains different sedimentary environments. And in fact, in this image, in general, you see the two major subdivisions. So in this first half of this group of lectures dedicated really to sedimentary environments, we are going to focus on the one that you have on your left, so the continental environment. So it's interesting to see that you have different locations where sediment can accumulate in a continent, and these usually will correspond to different transport mechanism, different flow dynamics. If you remember, in earlier discussions we were talking about the Froude number and also the Reynolds numbers, and looking at the influence that the flow velocity has in sort of influence in turbulence, and also the type of bed loads that tend to deposit. And so we started to discuss cross stratification and all those other structures. So they have a context. So in this case, for example, we can see alluvial fans on the top that are in correspondence of a major mountain range. So many times those cross stratification will be identifiable in those environments where we have major abrupt depositions. So these are interesting depositional environments, and in fact the early part of this lecture is really dedicated to that. And then the other major environment that we are going to discuss and that you will learn about is certainly the fluvial environment. So we will discuss a couple of types of environments, and these are the braided streams, so braided rivers, as well as the meandering. So we are going to talk about meandering, and so how the slope usually influences the evolution of a river system. Okay, so here of course you have many other environments, and we are going in future lecture to address some of these as well as you will recognize things like flatlands that contain abundant salt. So you have salt flats, playa lakes, things we have already mentioned in earlier lectures that, for example, were responsible for the formation of evaporitic rocks. So sedimentary rocks certainly are strongly dependent on where they form, and so we go from continental settings again into marine settings, where we find some analogies. For example, the alluvial fans here are matched by larger fans that are usually developed off the shelf or platform environment that is essentially the submerged top part of the margin of the continent. So we will see that we have different sediments that form in this platformal environment if compared to deep sea environments where we often have abyssal plains that are essentially influenced by things like the turbidity currents that we mentioned in earlier lectures. So the Boma sequence, so that's your canyon, and the flow actually of sediment that is accumulating very rapidly is often responsible for these characteristic things. Okay, we can move on and look at continental environments. So we're going to focus on fluvial environments firstly. So we are going to talk about alluvial fans and meandering a little bit also about braided river systems again, and also we will address aeolian environments, lacustrine environments, and glacial environments in sort of other lectures, or you will actually address those with your personal sort of interests and by reading about those environments, because we have limited time in this part of the course to address everything. So alluvial fans. Alluvial fans are usually abrupt depositional systems, so many times you have a subdivision really in an area where you tend to scavenge rock material and sediments, which usually result in canyoning and deformation of steep slopes on classic V valleys, or V-shaped valleys will often develop. You can see the V here. And these represent drainage systems that form in mountain ranges, which tend to sort of accumulate and collect a lot of the rocks that are fragmented through all those processes of weathering and erosion that we discussed earlier. So if you remember, we have those physical wedging processes as well as the chemistry of some of the reaction that dismember the mineralogy of sedimentary, metamorphic and igneous rocks, and they will lead to the accumulation in torrential systems of a huge amount of material that is then transferred usually to a lower level. Many times we find what is called an alluvial fan apex, which is where we have a major change in flow velocities many times. So you have to imagine water percolating through this valley at a significant speed. So as soon as you change the section of this river, so this channel will suddenly become much more extensive in terms of flow. So many times you have that this causes a major reduction of velocity, and so the carry capacity of this torrent usually decreases, and so you have the accumulation of major amounts of sediment. And this will be relatively ordered, especially in the peripheral parts of the alluvial fan. So an alluvial fan has usually two aspects. One is the active lobe, which is usually proximal to this major scavenging channel that is again a continuation of torrential flows, and usually on the sides we have levees that tend to form with a flow that is more laminar and will accumulate a significant amount of sediment actively. And so this is called the active part of the lobe. Many times the other parts instead are less frequently influenced by these discharges of water. So as a result of that, often you have development of vegetation and they get more stabilized, and so they are essentially inactive, or termed as inactive lobes. So remember, an alluvial fan is really usually an accumulation of sediment that is related to this sharp change in flow velocity, and it's commonly huge in terms of dimension. It can exceed the several tens of kilometers in some cases. So that's one of the primary mechanisms of transport of sediment when you are off a mountain range and you are more reaching sort of an alluvial plain where you have a sudden change in slope. So also important is the fact that you have major change in slope that also conditions the transport again, because if you have smaller slopes which are commonly on the order of 15 degrees on this top part, you will end up reducing significantly the velocity of flow. Let's see some other concepts. So modern alluvial fans, most common in areas of high relief, so we talked about mountain ranges. They can occur in different climates. So many times the most sizable are the ones that we find in desertic regions. They can also form off major fault zones. So if you have a big structural corridor, so even if you are not really in a mountain range, you can still have major offsets along major transfer faults. For example, in California, we know those faults, the systems that are close to San Francisco. So the San Andreas fault is an example. In those cases, you might actually have still availability of sediments that is quite substantial, and so you can still produce major fan deposits, alluvial fan deposits. So I mentioned the arid or semi-arid environments. These are environments where usually you have not much vegetation, and because of the seasonality you tend to have major torrential events. So these events are very disruptive, so they will lead to huge accumulation of sediments because of that. So what are the factors that really influence the formation of these important accumulation of sediment? Certainly topographic relief, so a mountain range, because of the gravitational energy. So gravity is a key factor here, and so you have major slopes also on those mountain ranges, which help with the transfer of sediment. When you have torrential rains, for example, you cause quite a bit of instability, and you tend to form those taluses that then are transported to major tributaries, and so you have this mechanism of transferring material very rapidly in the continental plains. Tectonically active catchments, yes, the source of sediment are those major tributaries, so off the main valleys you tend to accumulate. So you imagine you have sort of a system that has branches at different levels. So from the crest of the mountains you start to have quite a bit of catchments that develop, and those will start to collect the sediment, and then you have other systems that are of larger size that will collect even further sediment. So these are commonly called catchments. So they will capture all the sediment and transfer it downslope. A mechanism of transporting and alimenting the alluvial fan is necessary, and so you need, water. You need to have a drainage system that works to be able to construct your alluvial fan. Here is another example in an arid region. So probably this one is in the Death Valley in California, and that's a good example in which you have major salt flats. You can see some of the salts here, they're quite wide, so you have a connection basically with these flatlands which are highly desertic. You don't see any vegetation in here, and you have a major sort of mountain range here which is providing the sediment that is required to construct an alluvial fan of this type. So many times the shape is an apron shape, so it's triangular fan basically, which usually is thicker at the top and has very coarse material in the beginning, and then it finds out laterally because of the change in gradual change in flow velocity. So significant sediment production is certainly a key aspect for these, and so if you have a lot of vegetation and you're not in a region where you have no vegetation, like the Death Valley, of course you have to think that the trees, whenever there is some rainfall, will tend to hold the soil together with the roots. So there is preservation of material if you have highly vegetated domains. So here in Canada it's much more difficult to produce alluvial fans of this proportion because of that. So remember, vegetation is certainly a critical factor. So alluvial fans in arid or semi-arid environments will pass downslope into a desert floor, which are those flatlands, and you have sort of internal drainage such as playa lakes forming, which sort of collect the finer fraction of the sediment, and often they collect also evaporites. So remember that we have ephemeral lakes, so the playa lakes are ephemeral lakes, they are seasonal, they can the level of water can vary significantly, and sometimes they get completely dried out. In the humid environments it's different. The fans will tend to merge downslope with alluvial or deltaic plains. We will see some examples later of a deltaic plain. It's much more complicated. We have multiple branches that develop and they join with commonly tidal flats, where you have much more complex stratification of the sediment. So we find quite a bit of cross stratification in those environment, and also of the trough type. So trough like cross stratification is common. So it is also possible for fans in humid areas to build into other bodies of water. So in those instances you have essentially a marine fan that develops, or fluvial fans as well. Fans that build into standing bodies of water will be called fan deltas, so very close in concept to a delta, very similar in a way to the concept of a river that is rich in the sea. We will have a dedicated lecture with respect to marine deltas, so I won't spend much time on that. The climate really influences then the dynamics of alluvial fans. So their interaction with playas and floodplains is a good example. Cyclicity and the connection with the hydrological systems are the main distinguishing factors. Yes, because if you think of a desertic region, the cyclicity will be really critical because of the fact that you have flash flooding many times. So these torrential rains will be very periodic. They are not a constant process, and so cycles in which you have a lot of evaporation and scarcity of water will be alternated with these major torrential events. The contrary is true for humid regions, where you have pretty much a constant upward of waters, and so because of that the dynamics will be different. So there will be more water available, and so you will change also the sedimentary structures that you can form. This is another example of fans that is more braided, and again it forms in arid environments. Okay, let's have a look at a classical example that is rather tectonic. So in this case we have the effect of a major structure. So you can see here a fault zone that has some displacement. This is a normal fault. So many times you have escarpments that can develop really close to the apex of an alluvial fan. And yes, these often are events that are periodic in time, and so you can see the effect of the movement of the structure in changing the volume of material that is produced of this escarpment. So as a result of that, you get that the coarser fractions of the alluvial fan tend to propagate laterally towards the alluvial plain much more extensively. We can see also a different set of sediments here. So you have a legend here. So we have alluvial fan deposits in here in the near vicinity of the escarpment, and then we have floodplain related deposits, because in this case you have also a lake system that has developed. So you have essentially a river that is supplying water and is forming a depositional environment that is different from the one of the alluvial fan. And so you get more floodplain related sedimentation that is associated with these bodies of water. So in this case, there are also other things. So we have stream channel sediments and lake margin sediments that will be the result again of the movement of the riverbed over a certain extent. We talk about roughly 2 kilometers here for this scale, so you can think of these as a roughly 6 to 10 kilometers section, and so the water can travel also laterally. We can have changes in the position of the river system over time, and this results in a heterogeneous distribution of these stream channel sediments, which usually are coarser size sediments. So many times you have intervening of finer and coarser fractions when you have a fluvial system that is operating in a region. We have also much more organic rich material which represent the lake sediments, so finer fractions that are essentially derived from either the fluvial system or partly from this supply of sediment coming off the alluvial fan will be accumulated in the lake, and these finer fractions sometimes can be particularly rich of organic materials, and so they get extremely dark, especially if there are reducing conditions. So tectonics will certainly play a role in controlling the morphology of these features. So the extension, for example, of these lobes of sediments that is derived from the escarpment, again, are a function of the dynamics or the movement of these faults. Other aspects, I think, if we look at this example, we can certainly understand that alluvial fans are not a inhomogeneous deposit. They have well-defined zonality, and so they are certainly heterogeneous and homogeneous probably in this central part here, where we tend to have that the sediment load is particularly coarse, and so you can see these symbologies actually illustrating that. So you can see the variation in grain size while you move off the major stream that is providing the sediment load. So from the apex really we start to deposit the coarser fractions, and then we have a gradual fining out of the sediment. So we have also to remember that the sediment is related also to a major fault trace that usually runs orthogonally with respect to the orientation of the major stream that is providing the sediment. So the fault scarp is commonly present. We will see some examples of that, and it connects with the slide we just discussed with that extension of sediment related to tectonics. So this system is not stable. Many times we have migration, so we have migrating ephemeral or perennial channels, so they can move laterally, and also you have that the older parts of the fan often will be reworked, so we can get gulling because of rain, that is, so the precipitations can influence really the morphology and redistribute sediment as well. And also you have aeolian reworking that can occur, and also organisms and plants mostly will cause bioturbation and the development of soils in this environment, which are also important processes. You can see here the image of this migration. It's a nice figure that illustrates the braided nature of this alluvial fan, and this is the active part. You can see the water. Instead, these are sort of the older parts of the alluvial fan in which we have only preserved the sediment, but there is no longer drainage, and so you start to have some vegetation developing in the oldest part of the alluvial fan. So these are less modified parts of the alluvial fan. These are more recent, and this is the active part again. So in some cases, these major events will be termed hyperconcentrated flows. We will see some examples of the stratification of these hyperconcentrated flows, but they are really high energy event. Another type of flow that often occurs is the one that relates to water that is actually falling off the sides of these major channels, and so you commonly call it a sheet flow because it's more laminar and will tend to pervade laterally the alluvial fan, and that explains sort of the finer fraction redistribution. One example again from a desertic region here. This is very nice because it does show you really well the canyoning and the rapid transport with relatively high sloping of sediment of coarser size, and so we can recognize basically the result of the redistribution of sediment in the alluvial fan. And also you can see major escarpments here, so this linear trend represents those fault discontinuities that are commonly associated with tectonic movements that originate closer to the apex of the alluvial fan. In some cases, instability can occur also in the periphery, and in fact you see here major disruptions and formation of creep and normal faulting in response to the instability that is probably caused by the vehicles that are moving through this road that has been constructed over this alluvial fan. This could be one of the reasons, but of course you can have also other factors. So earthquakes sometimes will influence and destabilize parts of an alluvial fan. You have another major escarpment here as well. And also this is a desertic region. You can see how the more distal part of the alluvial fan is reaching an ephemeral lake that is in a stage in which it's all evaporated, and so you have massive accumulations of salt at the periphery of the alluvial fan again. So a nice example. It's instructive because it gives you sort of the idea of these coarser fractions in the canyon, which you can see, and that's sort of the more proximal part. So we have massive gravels many times that accumulate in this region. Then you start to have more mixing with some cross stratification, so you have cross bedding which is dominated by sandy or pebbly sandstones, and then you have conglomerates many times in this region. So you have a combination of gravel and planar cross beds that are found, which is represented by the finer fractions. In this other part, which is more distal, we commonly start to have more complex cross bedding. So again, if you have a fluvial system that is interacting with the alluvial fan, you will start to see those trough cross beds that are typical of transversal sections with respect to the direction of, or downstream direction of flow. And so this is interesting because you see a major change in the sedimentary stratification, which indicates a boundary basically between the depositional systems that are independent of the alluvial fan and this other system that is rather a hybrid or a mixture of alluvial fan deposits and fluvial deposits that are again independent. So remember that most of the fans really can be divided in three basic parts: the upper, mid and distal parts, and we saw all this complexity. So that means you will be able, by interpreting some of the sedimentary sections you see in the field, many times you understand where you are located with respect to the alluvial fan structure. Alluvial fans are sort of interesting because of their dynamics. They are also important because of the alluvial material that is collected in them. So many times production of concrete, for example, relies on abundant gravels. So if you know a location where a major alluvial fan is formed, certainly you can consider that as a source for construction material, for example. Understanding where the apex is important because you know that the coarser fractions will be located in that region. So if you have a paleo alluvial fan, by looking at the stratigraphy, you can understand the distribution of coarser fraction, which again has importance from the standpoint of understanding materials. The upper fan usually is this domain close to the apex, and it's the one that has the steepest part, so it's this one here as well. So it will be the one that is again represented dominantly by gravelly material. So many times these are sedimentary loads that contain quite a bit of mud because they are relatively immature. So you can form usually fanglomerates in these domains. And so these will be from partly to fully consolidated materials that contain a matrix that is dominated by clays. Okay, alluvial fans usually are subdivided in different zones. We saw that the proximal, mid fan, and also the more distal part, and we saw that we have different sedimentation rates. This is commonly associated with the slope, and so the fact that we have a higher slope in the upper fan many times is a key controlling factor for the movement of sediment. So we have as much as 15 degrees and the deposition of the coarsest fractions in there. Usually you have a central channel, and so we tend to have these as a torrential flow, so we have relatively high flow numbers in this region, and then in these other domains we tend to have sheet flow zones where we accumulate a finer fraction. So you have to think that always these regions are the ones that get the majority of the suspended load. Instead, the central part is in most cases represented by the coarser fraction, so the bed load. Okay, so streamflow is often confined to a single entrenched channel, and remember the composition of the material that accumulates at the beginning is quite often enriched with a muddy matrix. So we have fanglomerates that form, and this is because these sediments are relatively immature, so we have quite a bit of mud that is present. So you have irregular fractions, so we tend to have that the immaturity is represented by a very fine-grained matrix, and then we have larger cobbles that sometimes are even quite angular, so you can get rhyodites also in these domains. So we can see some examples here. You see essentially a fanglomerate, and the idea would be to try to classify the rock based on the observation that we already introduced in earlier lectures. So I could ask you if you think that this is a conglomerate, a diamictite, or a rudite, for example. And so we would have to look, at the percentage of the gravelly material versus the matrix of this assemblage. And in this case, the impression is that we have quite a bit of gravel in this case. So I would be inclined of either call this rock a fanglomerate that is similar to a diamictite, or a conglomerate, and this is based on also the level of rounding of the class, because there is quite a bit of rounding. If we move down in this zone, as I mentioned, we start to be in that's mid-fan area, so with the slope changes suddenly less than 5 degrees, and so we start to have combinations really of this coarser fraction that is in the bed load, and also these more sheeted flows zones that will represent those fine-grained fractions. So we start to have cross stratifications also in this interval. So how do they look like? And the question would be here, can you recognize any cross stratification in this sandy material? And the answer commonly is I don't know, but in reality it's a yes, because you can see here quite well the presence of cross bedding in this case, because this is centimeter scale is exceeded, so we have layers that are quite thick, and then you have an unconformity here and more planar bedding at the top. So classic bed forms that we discussed in the previous lecture, and they find the context in this case, which is a mid-fan context, and that's essentially related to this alternation of events, so the movement of these channels on the top part of the alluvial fan tends to vary essentially energy, and as a consequence of that you get different preservation of fractions. So there will be domains that are more gravelly with a lot of variety in fraction, and other domains that are more fine-grained, and they are sort of indicating also a different velocity of the flow, because if you remember, when we have cross stratification, many times that is sort of indicating a significant velocity of the flow, because you have to produce those ripples. Okay, so we had a phase in which the velocity was and the flow was diminishing, and we started to have more tabular beds forming, and then we repeat the cycles and we form another cross stratified layer on top, which is not visible in this example except for these. Probably these are actually part of the cross strata, but it's a big guess in this case. But yeah, you can see this cross stratification here, and this is reasonable. You can easily recognize this discontinuity. Distal fan is even more finer fractions, and we get more complex cross stratification. So in the distal fan or fan base, the slope will be much smaller, so less than 1 degree, and the sedimentation is dominated by these flowed processes, so mostly laminar flows of the main channel system. Usually this environment at the toe is grading into non-fan environments, so we can get cross stratification that comes off other fluvial systems that are independent of the alluvial fan. So that's an important thing to remember. So alluvial fans many times will be represented by these two characteristic stratification. So when you have a debris flow deposit, you will have this heterogeneous fraction. So usually the sediment is poorly sorted. We have a random orientation of the class, and most of the class are matrix supported, and we don't have any clear sedimentary structure in them, exception these scavenging surfaces or erosional surfaces that occur because they are recording multiple debris flows. On this side you have the sheet flow deposits, and this will have characteristic imbricated class. So you start from those cross strata in coarser fractions with imbrication, and then you have a fining up sequence many times, which is quite interesting because it suggests that you have a waning of the torrential phase. So you have that the flow progressively gets slower, and so it deposits much finer crack fraction because of that, because the energy is much lower at the top of one of these sequences. Characteristic is also the dimension, which is between the 0.5 and 2 meters many times. So the sheeted flow deposits will consist of these fining upward sequences. Instead, these deposits will be more debris flow type. If we look at the exceptional events, so the hyper-concentrated flows that we were mentioning earlier, we don't find really a major difference. It's better, this diagram is a bit better because it shows you more three-dimensionally the sequence, but again we have imbricated or cross stratification of coarser fractions here, which again are related to this very intense and abrupt events, and many times that energy is dissipated very rapidly, and so you lose the turbulence of the flow, and you start to have a switch from cross stratification into tabular stratification and also finer fractions. Many times the energy in the beginning is very high, and so often you form casting, and so you tend to have these channelized and major erosional unconformities that form, which will form those famous flute casts we mentioned. So the chute and pools, all those can be generated in this early phase and explains these major embayments. If we look at a braided fluvial systems, we will see that this is different. So this is a quite unique sequence that you find in alluvial fans. In this case you have the same example, so we have some myogenic sheet flow deposits. So these are more the low energy deposits, so you get much more finer fractions preserved, but they are again alternating between gravelly fraction as well as sandy fraction, which again supports this environment in which you have lower energies. So levee deposits are dominant in this example. So these are, again, it's a repetition, but this was a better sort of diagram to explain the structures that you commonly find in these deposits. So remember that those debris flows will develop usually distal stratified lobes, and so those stratified lobes will be more like this. Instead, the proximal deposits will be more like this because they represent the bed load, and instead this part here represent the suspended load, and this is why there is such a huge change in the dimension of the class. So in some cases, some of the debris flows we will get major blocks that can exceed the 8 meters easily in dimension, which you will never find in deposits that are rather related to suspended load. So the sediment accumulations in distal alluvial fans are somewhat similar to what is observed in braided rivers. For instance, they will have similar grading, but the key difference, because I mentioned earlier that they are different, is commonly the fact that these deposits will really lack the presence of bars, a concept that we illustrate in the next slides. But yeah, it's different. Many times trough stratification, especially cross beds of a certain type, will never form in these fan environments. So if we move into the braided river systems and we start talking about them, we need to look at the controls. So what happens in river systems that is different from the alluvial deposits. So the most important controls on the river type are usually the gradient, so the slope, and the presence of vegetation, and also the proportions in terms of bed load and suspended load. Commonly, the braided systems require a slope that is greater than 0.1 degrees. So we have relatively flat regions, but having a slope of more than 0.1 will be really sufficient for the development of braided river systems. So these systems are usually relatively straight, and if they get into situations where this slope decreases below that threshold, they can lead to meandering. So we switch essentially to meandering, which we will discuss in the last part of this lecture. Here you have an image that illustrates how a river system works. We have discussed this already in the past lectures. So the first one we had on sedimentary rocks, and we saw that many times we have different types of material that is transported in a river system. So we have suspended material, which is commonly a finer fraction and is subject to turbulence and is essentially above the critical velocity, so we can transport this fraction more easily at a specific velocity that exceed the critical energy required to suspend this material. And the other are fractions that are larger, and so you end up having more bed load that is moved through traction. So we have rolling, sliding, and saltation many times that is responsible for the transport of the coarser fractions. So if you look at an example of a braided stream, you can see a fairly extensive body of water, and many times by braided we means that we have a separation of the streams, which is a condition in which you form barren islands or islands that have quite a bit of vegetation when they have been developed for significant time, that represent your bars. So accumulations of sediment often separate essentially the stream, the main stream, in substreams, which are characteristics of this type of river system. So we can distinguish essentially braided stream because it usually has low sinuosity and it has numerous channels that are separated by these bars or islands, and commonly because of the high energy we have usually a good amount of sediment load, and it's also commonly represented by coarser fractions, especially in the main channels. So we tend to have quite a bit of gravel and also sand in these systems. A better figure here that shows these major islands of gravelly material and sandy material that is commonly found in braided systems. Other things that are key and well exemplified in this diagram, I think, is the cross stratification. So you see you have phases of variable energy, so you alternate between planar beds and more situations in which you have cross strata forming. So this could be either related to a change in the flow velocity or lateral transitions of the channels. So if they move laterally, many times you have a reduction in the flow velocity, or you lose completely the flow, and so you have a preservation of a pre-existing bed load. So in this case you see trough beds here forming, which are quite distinctive of this environment if compared to the alluvial fan. So again, the trough cross bedding is a key aspect in this case, and again it's linked to the bar development. So these are sand and gravelly bars which are quite unique. So we have here a better cartoon that sort of exemplifies the structure of a braided river system. So you have to think of three major domains of sedimentation. So one is the bottom of the sub-channels. So we have these multiple channels forming. So we will have the coarser fractions depositing really in these parts of the braided river system, and on the sides many times you accumulate more sandy material and gravelly material, which is a finer fraction if compared to the main bed load, and it forms these sandy bars or islands. So sandbars are the key distinguishing factor because they will generate trough cross bedding commonly. And so you see those lunated patterns because they are related again to the fact that you have much more movement of suspended load and bed load in the central part where you have the channel, and you left some of the sediments here that is not really transported at the same velocity. So this is why these islands are elongated. You tend to have erosive actions also on the sides, and that will shape them in this fashion. So this is the main depositional system, but you have also another zone, a third zone, where you deposit the finer fractions, which are these flowed plains. So sometimes you have spillovers of water with suspended load in the flowed plains, and so you tend to form what are called the overbank deposits, which are more tabular. The same type of cross relationship between tabular beds and cross stratification will be also formed depending of other two factors, which is either the movement of the channels that can migrate laterally. So you can see older and vegetated bars in this example, which are essentially pre-existing deposits that have matured and they are no longer influenced by the drainage system. And so you can recognize really these trough bands, which are quite characteristic. In terms of timing, modern examples are better preserved if compared to ancient examples. Definitely modern examples are better studied. Other things, braided rivers, they usually have a high proportion of sediment that is carried by rolling and saltation along the channel. I've already mentioned that. So you have essentially the floor of the channel that is collecting the majority of the coarser fraction. So these are commonly the placer deposits. And many times you find this massive accumulation of heavy minerals in those locations. Then we have bedload that is deposited in bars, and that's again more sandy or gravelly, which is because of the different level of energy. So this is how you form the braided river system, and this is why it's different from an alluvial fan. You will never have those sandbars forming, which is actually the largest features or type of sedimentation you find. So these bodies are quite extensive. Other things I would say are really the complexity of these mid-channel deposits. Sometimes they evolve significantly, so they get influenced by the channels that can go through them. So you have internal braiding that forms, so like this example here, and sometimes also more sinuous meandering, like this example. And so this is linked again with the variation in the flow velocity. So you can form bars, but also you can destroy them progressively if you change the flow. So in terms of flow velocity, we can see that flow is generally strongest between the bars, and the coarsest material will be transported and deposited in the channel floor again. So the larger class or coarse lag will be really in this domain here. Here you have again the finer fractions. So hopefully I repeated this many times so that it's clear in your head. And yes, this is another example we saw already when we were talking about the structure. So remember, these lunated patterns are quite helpful to identify the cross stratification of the trough type in which you have major turbulence that is contributing to the irregularity on those crests of the ripples, which leads to the formation of this unique cross strata, which is again the trough cross bedding. Okay, in this figure we see a nice example of stream piracy. So I mentioned that braided river systems can move laterally, so they're highly erosive channels, and so you see here a good example of this process. In essence, on this side we have that some of the existing channel has been left by the majority of the water that now has developed a new course on the right of this image, and so is basically invading all this agricultural land. So this image is also interesting because it does show the lateral extent. These type of systems are usually very shallow, but they extend significantly in their transversal section. Another aspect is that certainly the main channel is quite straight, but you have a significant degree of sinuosity in the sub-channels that are forming within the gravelly material and all the other coarser fractions that are commonly excavated by these secondary processes. This is also a quite a bit anastomosed river system, because you have that secondary channels are intersecting themselves significantly. So if we look at the stratigraphy of those sandbars, I think it's important to understand how sedimentologies tend to represent the information that pertains to the grain size and type of sediments that accumulate usually at the base of a channel, or again in those islands that essentially are formed either in a mid-bar or in a transversal bar. So in this particular example, you see a diagram here that shows a legend that illustrates different types of materials. If you look at this scale here, it's quite useful because it gives you the type of sediment, unconsolidated sediments, that is part of essentially a strata. So these are all the different stratas that we find in a sedimentary log of braided river deposits. So we have here more finer grain fractions, and you can see that because if you look at this line and you extend it upward, you are intersecting a level that is within the muds, and it's between a clay and a silt. So if you remember those fractions, many times these are the really fine grain materials that are definitely below the half a millimeter in terms of size, broadly speaking. We will discuss this in the labs for people that haven't really sort of taken the lab as yet. Just keep in mind that these are the finer fractions of fine-grained sediments, and these are the coarser fractions. So the sands and gravels will be the larger size fractions again. So when you have a line that is a curve, it's indicating that progressively you have a normal graded sequence, and this is the main part of a bar, for example. So this material is dominantly sandy, as you see. So you have a very fine, medium grain, coarse and very coarse sand in this classification. So we go from relatively coarse sands into relatively fine sand at the top. This symbology is, as you could guess, indicating the cross stratification. So we can see different levels of cross stratification, some ripple marks here at the top because you can see the classic crest, and in this level instead we have that alternating aspect which is classical of those levees and essentially bank deposits that are formed on the side of the main channel of a braided river system. So these are often influenced by vegetation, so you have some roots that are indicated in this on this side. So these overbank muds and thin sands with soils and roots are quite common at the top of these sequences. At the bottom, commonly an erosional surface, which is an indication of the overflowing, for example. So if you are again in a situation in which you were in an overbank deposit and then you have that the main channel is moving laterally through erosion, you will cause this formation of erosional surfaces, and then you start to have coarser fractions depositing because effectively you have a high energy environment that is superposing to a low energy environment. So if we review some of this context, at the base there will be an erosional surface which is representing the base of the channel, and this will be overlain by a basal lag of coarse class deposited on the channel floor. So this is the coarse fractions that are mentioned. As the flow is stronger in the lower part of the channel, the subaqueous dunes and hence the cross beds tend to be larger at the bottom of the bar. So we have essentially that the amplitude of some of this cross stratification will be essentially showing larger dimension of these features because of the energy. So it decreases basically in set size while you move upward as well. And the last thing is that the finer sands or silts will be found at the top because these represent essentially the abandonment of the bar when it is no longer actively moving. So this could be one possible interpretation, but also the fact that you have the possibility of forming overbank deposits is also quite interesting as a possible interpretation. So multiple possibilities, but yeah, important to realize that we have different level of energies in a braided river system, and this will correspond to different fractions and structures we find. Okay, so let's move. Here we have other comments. So the deposits of gravelly braided rivers are commonly characterized by cross-bedded conglomerates representing deposition on channel bars. So this component here can have quite a bit of gravel and cross stratification as mentioned, and sanded braided river deposit typically will consist of fine in upward succession, which is what we have already mentioned as well. So we have essentially that from a sharp scored base, so the erosional conformity, we go into trough beds and essentially move then into more planar cross-bedded and laminated materials. So these find easy explanations if you look at the different depositional environments. So if you remember, I was mentioning that three-dimensional cartoon earlier with those three distinct settings. So remember, when we are at the bottom of a channel, we usually get the coarser lag, and that's the first depositional environment. On the side or in the middle, we split the channel system with a mid bar or a transversal bar sometimes, and this will be more sandy accumulations and gravelly accumulations, so you form an island. And the third environment where we have deposition, which is more suspended low at deposition, which explains this stratification with finer fractions, is this overbank deposits which happen to occur when we have spillovers in major flooding events that occur on a braided river system. Many of the dynamics that occur in braided river systems, remember, is really related to this fluctuation in flow. So if you have a major flooding event, you will end up having changes that occur. So for example, you destroy some of the sand or gravelly bars, or you have that you subdivide them, so you change their morphology, or you have spillovers in the banks, so you form new overbank deposits that are more mudded, and so all these processes really do not really happen continuously. There will be a function of the cyclicity of the load, and so bed load and suspended load will change as a function of major flooding events, basically. An example that is even more complex is this one, in which we have, to sum it up, an alluvial fan, but on top of that alluvial fan we developed a secondary system of braided streams. So you have braided streams that are essentially eroding away the pre-existing fan. Many people think that these alluvial fan are produced with these braided systems, but in reality it's the other way around. So these are sort of relatively constant flows that can occur, and they will erode away the pre-existing fan deposits, which were instead deposited in very abrupt events that were chaotic and storm-like and quite unique. In fact, it's many times estimations suggest that major alluvial fans can form roughly every 300 years. So this type of continuous braided flows, which are more seasonal if you want, they will have more an erosive action and redistribution action on the alluvial fan, which is interesting to know. If we move now into the meandering river systems, it's important to realize that these systems are distinguished usually based on the amount of suspended load. So these rivers usually are, of course, have a slope that is lower, but they have much more suspended load. So a very impressive erosive action, which is also linked to the inertia of the body of water, because these usually are systems that have deeper channels and more stable banks many times. So the erosive action is often leading to a characteristic depositional system, which is responsible for the formation of what are called meanders. So meanders are directly influencing an important property of these river systems, which is the sinuosity. So remember, the sinuosity can be calculated with a simple ratio, which is the ratio between the tallweg length, which is essentially the line that connects all the points that are at a lower level within a river system. So it's a sort of a curved line, and the wavelength, which is essentially the distance between a couple of crests, if you want. So if you get a couple of meanders, you will calculate that linear distance. So of course, if the river is really sinuous, this ratio will tend to increase, and commonly it's above 1.5. So classification for meandering systems is usually systems that have a sinuosity that is higher than 1.5, which is again this characteristic ratio. So what this is telling me is that these are highly erosive systems, because the sinuosity is the result of a process in which we have essentially that where we have the tallweg, which is on this side, we usually have the maximum velocity of the flow. So this is called the cut bank, which is a region in a meandering river where the sediment is essentially sourced. So we remove sediment, so assuming that the flow is going in this direction, so the water is moving from this domain to this one here. What happens is that the sediment will essentially be moved progressively to the downstream location. And so if this is the high velocity domain, this other bank is forming a floodplain, and it does have essentially accumulation of relatively finer and sandy fraction. And so the process leads to the growth of this side of the river and the progressive erosion of this other side. So again, even in these systems, we have a range of deposits that form in response to this sort of alternating action of erosion and deposition. So we have lateral accretion that will form transversal cross stratification, which is quite unique. And then you have a combination with planar strata, so you have major discordant layers that form, in which you have sort of adjacent lateral accretion and formation of overbank deposits, which are related to these spillovers again, so which are commonly called the crevasse splays, which are mostly suspended load that deposit in these floodplains. So you get major flooding events, and this will be characterized by unique sedimentary patterns, which we will review at the end of this lecture. For example, those climbing ripples I was mentioning in earlier lecture. So if we have to fit structures into place, in this case we will have characteristic cross stratification of gravelly and sandy materials and more claystone material that forms tabular bedding. And also, since these are quite abrupt event, you have a major input of sediment, and so we have a system that get essentially invaded by abundant sediment, and so you have cross stratification that can form, but we have ripples that will climb rapidly because of the high sediment supply. So when you have this lateral cross stratification, you will form bars, and these are commonly called point bars, okay? And the accumulations on the side can be also commonly called accumulation over levees. So that's also another important term to remember. So if we summarize, meanders developed by the erosion of the bank closest to the tallweg, which is the deepest part on the river, and it's where you have the highest velocity, accompanied by deposition on the opposite side of the channel, which I've mentioned. The position occurs where the flow is sluggish. So yes, the velocity here will be slower in the internal part. And the bed load can no longer be carried because of that, and this is why you form those accumulations. We continue the erosion of the outer bank and deposition of the bed load on the inner bank. The channel will develop these characteristic bends and the meander loops. When the bends progress over time, we will see in the next few slides that we can form major loops. The deposits of a meander bend develop a characteristic profile of coarse material at the base, normally sands and fine gravels, becoming progressively finer up the inner bank. That's true. So most of the initial stuff will be coarser, and then you move up and you get finer fractions again. So hopefully this clarifies some of the key structure and sort of key characteristics of meandering at the level of the type of deposits. We have really a range of other factors that will be characteristic of these domains, but I think this is even sort of further complicated things. But if we move out from the main channel, which you can see here is developing a classic laterally accreted point bar system, you have to again take into account also the development of these spillovers or splay and crevasse deposits, which will be quite important for the identification of these sedimentary deposits. So these crevasse splays and also floodplain deposits will be most distal facies, and so they will be mostly represented by fractions that are relatively fine, both because of the transport that they incur and also the fact that they're dominated by sediment that is coming from the suspended load. So they are quite important still, and they represent again a relatively low energy environment, which justify the grain size and level of sorting you find in these sediments. Okay, so if we move on, we can see how the erosion proceeds, and so you get some initial looping that you can observe in this cartoon, which is quite interesting. So you can see how the flow here is essentially leaving this domain at a low velocity range. So we got, in this case, at the inflection point, this is how it's called, so which is essentially a mid-range point between the two maximum curvatures of the meanders. So it will be in this location. You tend to have that the maximum velocity will be in the central part of the stream, while you move closer to the high curvature domains, which is the meander, you tend to start to erode away things and deposit internally things which come off this other erosional zone. So sediment will be moved from this domain to this region, and also the velocity is moving, so you have high velocity on the external part of the channel, and this gets repeated over and over. And so we have a process in which this meander is essentially moving outward, as well as this other, and sometimes they move in a direction that is concordant. We will see that with some other images. So here we have some examples that are a real case example that shows the different deposits. So you have the point bars that are well exemplified. So they are located here, so you can see the accumulation of sandy material in these low velocity domains, and in the high velocity domain we have quite a bit of erosion that is sort of influencing some of these bank deposits. So again, the point bar will develop laterally, so you will have essentially a stratigraphy that is represented by gravelly material at the bottom, and then you have cross stratification of sandy material that is quite characteristic. We saw the image just before, and then on the top we form those crevasses or splays, which are again represented by finer fraction and suspended load. So hopefully it's clear now the classical stratigraphy you will find and the type of structures that are common. So it's still normal, but you have quite a bit of cross stratification that is transversal with respect to the downstream direction, and it's quite unique. So you form quite unique sandbars, which are again characteristic of these meandering systems. So if we look at the stratigraphic sequence, so with this characteristic representation here, we definitely see what we're already sort of mentioning with respect to the normal grading. So we tend to have coarser fractions at the bottom and then more sandy materials, and we can see also a transition in the type of structures that we have observed also in braided river systems. So it's very similar in a way. The type of stratification that we find in sandbars will be also found in these meander related bars. So channel fill will fine up progressively, and also the dimension of the features you find will be reduced because you are lowering the energy. So in the top part you form the ripples, and then you have again those overbank deposits that tend to form with the vegetation, and again the evidence of an alternating pattern in which we tend to have mostly clays and silty materials. The interesting aspect is in this environment we will find also the mud cracks. So those symbols are indicating the presence of mud cracks, which are an indication, I think, of the fact that this supply of water is really related to flooding events that essentially cause these crevasses to form and spillovers of water again that is particularly enriched in suspended load. So again, repeating some of the things we have already seen in the previous slides, this is also illustrating the type of cross stratification and indicating that we have sort of an initial phase of lag deposits, so very coarse fractions, gravelly material, and then more sandy material that forms trough cross bedding or ripple cross laminations on the top part with these overbank deposits. Okay, if we move on and look at this example, we are starting to sort of appreciate the complexity of the meandering. And so in places where the bend in a meander will exceed essentially the angle of 180 degrees, so in entire sections of the channel during a flooding event can become abandoned because we have essentially instabilities that will occur. So this is a relatively complex process, so we're going to see some images that illustrate it a little bit better than this diagram, but I think it's important to realize that these meanders have a certain dynamic, so you will have active channels that are operating and also other cases in which part of the channels are abandoned. And so we need to understand why this is occurring and why we form things such as oxbow lakes, which are abandoned meanders that has still some trapped water in them, so they become lakes. And also you see in section how these channel fills, which are these cross trough bends that we find in meanders, will tend to get accumulated at different levels and in different locations. And this is of course related to the dynamics of this process. So the fact that the meanders are moving in space. So the question is, how can we form lakes like this, so oxbow lakes, and this is commonly called the process of cutoff of the loop of a meander. And so it's again related to the dynamics of the meander and the evolution of a meander system. So many times we can schematically represent a cut bank erosion process with essentially two meanders that are moving in opposite directions. So you are moving essentially through this development of point bars and erosion on this flank. We are moving essentially this meander in this direction and this other in an opposite and contrasting direction. So at some point they will be really close to themselves. And so that will cause this phenomena in which we have what is called a jump. So you tend to have that you cut the side of the meanders and form essentially a connection, and so the water will start to go through the shortest route and will leave the oxbow lake formed. So we can see some better images of this process. So if we start with a sinuous river system, we can progressively sort of form areas where we have maximum erosion and maximum deposition, and then we progressively increase the sediment deposited on the low velocity domains and gradually erode and increase the sinuosity of the meandering system. You can see how the meander develops gradually, and at some stage the distance here is becoming very short, and so we can see that at that point we have a break. Of course this breaks because of flooding events, so you get a major flooding event, and so you have a major erosional condition related to the for example turbulence of the waters. So major inputs of water and sediment will contribute to the erosion of banks and can lead to a complete change in the course of major flows and change in the morphology of channels. So the oxbow cutoff is forming in that location, and then you have the oxbow lake on the right as a result of this process as well. So in definitive, we can conclude that these are dynamic systems and they are well represented through the stratigraphic record, because if you think of systems that abandon their course, all that stratigraphic record gets preserved in the history of the rocks if it's no longer subject to erosion and reworking of a drainage system. So cross stratifications that are commonly found in these meandering rivers can be recovered also for example from Devonian times, so relatively ancient times. So both alluvial fans, meandering rivers will have good preservation chances, and so you can recognize them in older stratigraphy, ancient stratigraphy, and this can have also implication for the discovery of important mineral resources. For example, many of these meanders can host quite a bit of organic matter, so vegetation that gets trapped, and many times we find uranium deposits in paleo channels that have been preserved through the geological history. The same is true for petroleum accumulation. Sometimes you have abundant shales that can form in this context, and so you might preserve also petroleum as well. So if we conclude this lecture, we look at the flood plains. So you have beautiful examples here of climbing ripples at the bottom that give you an indication of the energy of this environment. So we reduce the grain size. So if you remember some of those diagrams that I was showing that were comparing flow strength versus grain size, certainly as soon as we have a spillover, you tend to have a rapid decrease in velocity of the flow, and also we have finer fractions because the majority of the sediment is again represented by relatively suspended load, so most of it will be suspended load materials. And so we have silty fractions in the beginning, very close to the main river channel, and then progressively while we move away we'll get more clay materials forming. So sand and silt deposited usually as thin sheets over the float plane, and remaining suspended load will be deposited in flood waters and dry out after the flow has subsided. And this explains why you find also mud cracks often in these environments. So again, these will be laminated deposits because they are represented by a significant amount of cyclicity, and so they are seasonal, and also they are related to major flooding events, and so this will result in significant lamination in the sediments. And also the fact that we have big loads of sediment will often lead to migration of ripples, as illustrated again. So the primary depositional structure that are observed in these flood plains will be thin beds, which are normally graded. There will be evidence of initially rapid flows, which usually is accompanied by relatively flat line lamination, and then because of the waning you reduce the energy and you start to enter in the realm of ripples. So you get climbing ripple lamination, and then you have thin sheets of sediment that will form again when you slow down even further these flow events. And there will be also erosive processes that can occur usually at the base where you have mostly sandy materials. And these are commonly located really near the channel where the flow is most vigorous, so it's where you have the spillovers. And the last couple of things are certainly the desiccation cracks and the fact that you can form vegetation in these regions, so you will end up forming soils. Okay, final slide with some questions that it's important to you review. They could end up in your assignments, or I could actually ask some of these questions when we have the oral examination, which is the last part of this course. With respect to the program, I think we have completed the continental environments. We are left with marine settings. We have still some discussion that we need to do about fluvial systems when they meet the sea. So deltas and estuarios will be object of discussion, and also we will discuss the littoral environment where we find shelf settings, neritic zones, platforms, and all those different type of sediments that are more carbonate rich. So we will discuss also those to complete our sort of interpretation of different depositional environments that are characterized by sedimentary rocks.